Hi everyone. In this video, we're gonna go over the exercise questions for chapter 5. There are 3 of them, so we will get started with the first one. The adjusted seasonal indices in the following table reflect the changing volume of businesses of the Mount Spokane Resort Hotel, which caters to family tourists in the summer and skiing enthusiasts during the winter months. No sharp cyclical variations are expected during 2007. A multiplicative component model is used to fit the data from January 2000 to December 2006. And then, so you see the table here showing you the seasonal indexes. There are 2 parts in this question. A, if the linear trend is t equal to 140 plus 5t, what is the trend forecast for the first month of 2000? B, if we assume CNI to be 1, what is the forecast number of tourists for the first month of 2000? So in this question, we do not need to use Minitab. Actually, we just do the calculation manually. Basically, we have a decomposition model fitted to monthly data for 6 years from 2001 to 2006. We are given the seasonal indices and the trend. We want to focus for the trend first, then we want to focus for the time series, which is the number of tourists for one period ahead. So before we start solving this problem, I would like to draw your attention to the seasonal indices in this table, okay? And you would notice that the seasonal indices in table are 120, 137, until 97. If you can recall from what we saw during the lecture for chapter 5, the indices there we used is 1 point something or 0 point something. So these 2 indices are in 2 different scales. What you see here is, to a certain extent, is kind of like a percentage. So for January, that's 120%. And therefore, when we really carry out the calculation, we do want to convert it back to 1.2. That's the way to use it. Indices are supposed to be technically somewhere around 1. So it started from 1, meaning this is the same as the average. If it's above 1, that's above average. If it's below 1, it's below average. But when indices are scaled to hundreds, that basically means percentage. In that sense, values above 100 or above 100% means that's above average, such as January, February, not March. March is exactly the average. And values below 100, 100, or 100% indicate these are months that are below average, like April or May. Okay. So let's start with part A. For A, we are given the linear trend, and we know that data ranges from January 2001 to December 2006. So we want to first determine the number of observations. Then we can determine the value for the lowercase t for one step ahead. And since we have 6 years of data, and in each year there are 12 months, so that means we have 72 observations. And therefore, the lowercase t for the first month of 2007 should be 72 plus 1, which is 73. Okay. Now we can do the trend forecast. Trend forecast is, we have capital T equal to 140 plus 5 times t. Technically, there should be a little hat above t. I'm gonna manually write it later. So now we have 140 plus 5 times 73. Going through the calculation, we've got 505. Okay. So that's the trend forecast for one step ahead. For part B, we want to forecast for the number of tourists, which is the value of Y for the first month of 2007. And the model is given to us as a multiplicative model. So Y is equal to T times S times C times I, right? So all components multiplied together. For T, we're gonna use the trend forecast, which is 505. For S, we're gonna use the seasonal indices. Instead of using 120, we want to use 1.2. And just a quick note, you may ask, how do I determine if it's 120 or 1.2? Well, whenever you use seasonal indices, you look at the overall values. If they're all around hundreds, then you know you want to change them or convert them into decimals values around 1. So 120 should be 1.2. Okay, but if you look at the values, they are around already numbers around 1, so 1.05 or 0.89, etc. Then you use the number themselves. Okay, so back to our forecast. Seasonal indices is 1.2. The C component, cyclical component, is 1, as given in the question, and the irregular is 1. In particular, we know this is true because it says in the question that no sharp cyclical variations are expected during 2007. So if you carry out the calculation, we have 505 times 1.2, and the answer is 606. So that will be the number of tourists for the first month of 2007 using this decomposition model. All right, so that's question number 1. Now we're gonna move to question number 2. Question 2 says, table P16 contains the quarterly sales in millions of dollars for the Disney company for the first quarter of 1980 to the third quarter of 1995. There are 4 parts of the question. A says, plot the quarterly sales time series. Do you think an additive or multiplicative decomposition will be appropriate for this time series? Explain. Part B, does there appear to be a significant trend or seasonality? Would you use both trend and seasonal components to the forecast? Part C, perform a decomposition analysis of Disney sales. Interpret the seasonal indices. Part D, forecast sales for the fourth quarter of 1995 and the 4 quarters of 1996. All right, so we're gonna hack to Minitab because we do need to run the models and get some plots to answer the questions. I've already copied and pasted the data from Word document. If you haven't done so, you can find the data in the data file, chapter 5 exercise data. Open that file, copy the data, and paste it to Minitab. Then you will see 3 columns. The first column denote the year, the second column denote the quarter, and the third column denote the actual sales. So we have quarterly data. Part A says to get the time series plot. So we're gonna go to Stat, Time Series, and pick Time Series Plot. The data will be sales, and click OK. Let's examine the pattern. Actually, in this question, the pattern is very clear, right? We can see upward trend in the data going that way. We can also observe seasonality, especially if you look towards the end, the seasonal pattern is very apparent. Now we get to determine which model we want to use. Is it the additive or multiplicative? Now, since we can tell that the seasonality the variation is increasing towards the end and it's not constant, so we can determine to use multiplicative model. And that's for part A. So the answer might be a multiplicative model is more appropriate since we observe increased variability towards the end of the data series. All right, so that's part A. For part B, we want to determine if there's trend and seasonality. I've already briefly talked about it. So for part B, we observe an upward trend in the data and seasonality. So we would include both trend and seasonality in the model, right? Part C, we want to perform a decomposition analysis of the sales, and then we want to interpret the seasonal indices. So basically, we just want to look at the seasonal indices and determine what seasons are high seasons, what seasons are low seasons. So let's do the decomposition now. We're gonna go to stat, time series, and we're gonna pick decomposition. The variable will be sales. Seasonal length is 4 because this is quarterly data. And we will use the multiplicative model. We will also include trend and seasonality. Then we just click on OK. Or if you remember, in the last step, we do want to do the forecast. So you may want to do that all at once, and the number of forecast will be 5 because we're forecasting for 1 quarter plus a full year. So I put 5 there and then click OK. All right, now we got the model, we got the data. This graph is a little bit messy, but you can still see that the blue line indicates the original data or the actual data. The green straight line is the trend, and the red one is our forecast. You would see at the beginning, the red one is almost identical to the green line, but towards the end, we see more variation out there. And at the end, the purple ones are the forecast. So the next thing is we want to interpret the seasonal indices, and that is part C. Now we look at the seasonal indices. It seems like the second season and the third season are relatively better seasons, and the first one and the fourth one are relatively slow. However, a non-linear trend may work better than a linear trend. So we can tell that the decomposition with linear trend may not produce the best results. So that's part A. And for part B, we want to answer the question about trend and seasonality. So we will say, for part B, I'm going to type on this side. B. We observe both trend and seasonality in the time series plot. Therefore, both components should be included in the decomposition model. So that's part B. And part C, we want to perform the decomposition analysis and then interpret the seasonal indices. We already observe strong seasonality. We just want to use the seasonal indices to determine what seasons are the high season and what are the low seasons. So I'm gonna go to stat. And it's a little bit messy, so I want to clear everything. So I'm gonna go to stat, time series, and pick decomposition. The variable will be sales, and the seasonal length will be 4 because we have quarterly data. And we want to use multiplicative model. We also include trend and seasonality. If you remember from the question, we will be asked to forecast for the fourth quarter of 1995 and the 4 quarters of 1996. So that's a total of 5 quarters. And therefore, we want to click on generate forecast and fill in 5 so that we don't need to estimate the model one more time. Click OK. So there we go. We got the results, the decomposition for the data. And in part C, we want to focus on the seasonal indices. Before that, I want to pull down the results and just visually examine the graphs. Now, if I look at the results, this graph, it tells me clearly that this straight line linear trend does not represent the original data that well, because at the lower end is underestimate the data, and towards the upper end, it will be underestimate the data as well, and in the middle, it overestimate. So again, it seems like a nonlinear trend will be more appropriate. So back to the seasonal indices. For part C, so we're gonna say based on the seasonal indices, we can tell the following. If you compare the numbers, you notice that for season 2 and season 3, the indices are above 1, meaning that these 2 seasons are high seasons. The sales in these 2 seasons are above average. And for the first and the fourth season, they are not as high as 2 and 3, so they are low seasons. And therefore, we can write down, we can tell that season 2 and 3 are high seasons, since the indices are greater than 1, and season 1 and 4 are low seasons since the indices are below 1. Right. So the seasonal indices double confirms that what we observed in the time series plot, there are seasonalities in the data. And for part D, we did the forecast, but we also notice, if we pull down the results, you'd also notice that if you look at the purple dots, they are the forecast for the next 5 quarters. In comparison, here are the last few observations. They are much higher than our forecast for the next couple of quarters. And actually, that doesn't make much sense, because overall, if you look at the overall pattern of Disney sales, it is increasing dramatically. It is increasing gradually, not dramatically. And towards the end, it's getting higher and higher. However, our forecast will be lower even than the previous years. You would expect sales to continue increase unless you have other reasons to say the revenue or the sales for Disney for the next year, it will not be good. But that has come to but that has to come from outside this model, and we don't have that information. And we end up with lower estimates, all because really is our linear trend. And therefore, actually, another trend will be much better, or another model will be better. So I do want to type a couple of comments for part D. The forecast from decomposition underestimate the sales for Disney, since the forecasted sales in future years is even lower than sales in the couple of pre-years. Okay, so that's part D. We're gonna move to question number 3. So table P25 contains the number in thousands of men 16 years of age and older who were employed in the United States for the month from January 1993 to October 2003. Part A, use the Minitab to do a multiplicative decomposition of these data and generate forecast for the next 12 months. Does a multiplicative decomposition appear to be appropriate in this case? Explain. B, is there a strong seasonal component in these data? Are you surprised? Do the forecasts seem reasonable? Part C, the default multiplicative decomposition Minitab assumes a linear trend. Plot the employed men data in table P25 and examines the years 1993 to 2000 and 2001 to 2003. Is a linear trend appropriate? If not, can you suggest a trend curve that might be appropriate? Fit your suggested trend curve and store the residuals. Compute the autocorrelation function of the residuals. Do the residual autocorrelation suggest a seasonal component? Explain. All right, couple of parts in this question, and actually this question combines several things that we learned together. Instead of examining the data first to determine the decomposition model, it tells us what decomposition model we need to use. And then we examine the seasonal component. Then we would focus on the trend. As you may be able to sense from the questions, the linear trend probably will not work well for the data. And that's why we want to examine it more carefully. And even in part D, we want to fit a different curve for the trend. So let's move to Minitab and carry out the analysis. So I've already copied the data, and there we go. We have 3 months, start with year, month, and number of men employed. We start with the decomposition directly. So we're gonna go to stat time series, pick decomposition, and this time the variable is number of thousands, the number of men employed. Seasonal length will be 12 because it's monthly data. In particular, the question didn't tell us whether we want to include trend and seasonality. We will, because we want to be inclusive in case there's trend and seasonality. Actually, if we plot the data, if you bother to do so, you will find that there is trend and seasonality. Maybe not a linear trend, but since we don't have other choice, we're gonna include the trend. Also, the question asks us to do the forecast for the next 12 period, and therefore we will select general forecast and put 12 there. Then click OK to get the results. So there we go, that's the results. For part A, we want to comment on the decomposition model, whether it's appropriate or not. I'm gonna move to the graph. and look at the data, the trend, and the forecast. Okay, so in general, I would say the decomposition does an okay job. However, it's a little bit messy here, but if you look carefully at the very beginning, the decomposition tend to overestimate the numbers, and towards the middle, decomposition underestimate the numbers, then overestimate again. In that sense, we would say the decomposition model is okay, but not quite good. Really because we only have one option for the trend, which is the linear trend. So part A, we would say the decomposition is okay. However, the linear trend in the model may not be appropriate. Let's see, the decomposition model tend to overestimate the data, the series, towards the end, and therefore the forecast overestimate. All right, so and furthermore, if you don't see that, let me show you a little things right down here. These blue dots are the actual data, right? And you will forecast for the next 12 months, we see the same pattern. However, for the purple dots, they are much, much higher than the blue ones. And you would not expect such a big shift. If you look at the pattern before, the seasonal up and downs shift a little bit from year to year, but wouldn't shift this much as forecasted by the decomposition model. For part B, we want to answer the question about seasonal component. Even from the graph, we can tell there is strong seasonality. So for part B, we'll say we observe strong seasonality. We can also confirm that in the seasonal indices. And I would copy and paste the seasonal indices table below that, which is given here. If you look at the indices, we have values, especially from May to October, right? The seasonal indices are all above 1, meaning these are good seasons. And starting from November to April, these are slow seasons. But in the data, we're talking about employment, right? This basically just tells us when the weather is warmer, we have more employment. And during winter season, somehow we have relatively low employment. So continuing with part B, a question asks, are we surprised? We're gonna say it is not surprising to see that May to October are high seasons with higher employment, and well, November to April are low seasons with lower employment. That suggests that the weather can affect employment. So that's that. It also asks whether the forecasts are reasonable or not. I do not intend to repeat the same thing since we'll answer that in part A. We pointed out that the forecast from the decomposition tend to overestimate the values. Then part C, we want to do the time series plot and focus on the trend. So let me clear everything. So we're gonna do stat, time series plot. And the variable is C3. And the variable is C3, so click OK. Then we've got the time series plot. All right, so the question is a linear trend appropriate? I would say yes, for all the observation and to that part, it's basically a straight line going upward. After that, we see actually the trend is leveling off. So that's another trend. And therefore, one thing we can confirm is that the linear trend is not appropriate. The data is actually split into two sections. As the question suggests, we can also confirm in the time series plot. This is probably year 2000 around. So before 2000 is an upward straight line trend, but after 2000 it's leveling off. And therefore, for part C, we're gonna say according to the time series plot, a linear trend may not be appropriate. For 1993 to 2000, we do observe a linear trend going upward. However, for 2001 and 2003, we observe a different trend and the data seem to have leveled off. So that's part C. Now the part C also asks us to suggest a curve that might be appropriate. If we have to pick a curve, then I'm gonna want a curve that looks like that, right? So it's a reversed level curve. And if you can recall from the lecture, that is the quadratic curve. So we're gonna, for part D, fit the curve and see what happens. Let's go to stat, time series. This time we're gonna do trend analysis because that's the option we have to pick other curves. And the variable is C3. Now this time we're gonna pick quadratic one. And then the question also asks us to examine the residuals. Therefore, we're gonna go to storage, check on residuals, click OK. OK again. So there we go, that's a quadratic term. Let's see. Well, I would say this is better, not very good, but at least it's better than the straight line, the linear curve, right? Towards the end, the quadratic curve still tend to overestimate, but is slightly better than the linear trend. So for part D, I'm gonna say a quadratic curve is estimated for the data, and it is better than the linear trend. Then we want to also examine the residuals. So we will go to stat, time series autocorrelation because we want to obtain the ACF curve. And remember this time the variable is residual. So click OK. Let's see what happens. What it tells us. So let me pull up the numbers. You would notice that right down here, the highest one in the middle, that's lag 12. And this one, the one in the middle, that's lag 24. And also remember when we look at the seasonality, we determine that the summer seasons are high season and the winter seasons are low season, right? So we do observe very strong seasonality, which is also confirmed by the autocorrelation graph for the residuals. And that reason is we only fit a quadratic curve. We didn't take care of the seasonality. And therefore, the seasonality will show up in the residuals. That's what you observe there. With that, so we're gonna say, continue with, for part D, we're gonna say, we observe strong seasonality in the residuals. Things the autocorrelation in lags 12 and 14 are 12 and 24 are much higher than the ones before, than the ones come before and after them, right? So that's all we have for this chapter's exercise. Let me know if you have any questions. And that's all I have for this video.